Well, good afternoon. My name is Manfred Trummer. I'm the chair of the mathematics department. It is my great pleasure to welcome you all here and our worldwide audience to our second talk in our series on global warming, a science perspective. This is an event which is put on by the Faculty of Science at Simon Fraser University. And we are very pleased today to have as our speaker Professor Ken Golden from the University of Utah. It's a bit of a challenge to introduce various speakers for various reasons. In Ken's case, the challenge is to keep the introduction sort of below any kind of reasonable amount of time, because there's quite a bit to say about him. So I will keep this very brief. Ken got his PhD at the Courant Institute. He then was a postdoc at Rutgers and assistant professor at Princeton University. And he's been at the University of Utah since the early 1990s. Ken is the hallmark of he is an applied mathematician. And the hallmark of a really good applied mathematician is that many of their publications are actually in journals which are not mathematics journals. And that is true for Ken as well. His interests is quite an interesting list. It's sea ice. We're going to hear about that today. It's climate change. That's partly why we invited him here. Composite materials, phase transitions, and inverse problems. Now, in his talk, Ken will put these things together for you. One of his big claim for fame, of course, is that, as I think he likes to say, he is a bipolar person. He is a mathematician who has been to the Antarctic 6 times and to the Arctic 5 times, and he will be going there again soon. Now, I don't think there's many other mathematicians out there with that kind of record. One thing he hasn't been responsible for is, of course, the golden section. I should put that in case you thought that was named after him. But you will hear today about the rule of the fives, and as mathematicians we look forward to that. So high five for Ken, and I hope you enjoy the talk. Thanks.
Well, thanks very much, Manfred, for that wonderful introduction. It's really a pleasure to be here. It's actually my first time to Vancouver, so it's a great opportunity to see your beautiful city here. So the evidence is clear that our climate is changing, and it's changing perhaps most rapidly and most evidently in the polar regions. So I'm going to try to tell you about this, and also about some of the kind of work that we've been doing from the mathematical side to try to help understand what's going on and what may happen in the future. And so you'll see, as Manfred said, I've been to the Antarctic 6 times and the Arctic 5 times, and you'll see a lot of photos from both the Arctic and the Antarctic. And at the end, I'll be showing you a video from one of our Antarctic expeditions. This is a photo starting off showing some of the first-year sea ice in the Antarctic. And so, first of all, what's this all about? Well, it's about the cryosphere, the frozen part of Earth's surface. In the southern part of the cryosphere, Antarctica, we have this massive glacial ice sheet up to, say, over 2 miles thick, which is basically, now Antarctica is a desert, actually, so this is snow built up over millions of years. It gets thicker and thicker and thicker, and it gets heavier and heavier, and it turns into sort of ice that flows. And then surrounding the continent of Antarctica, out in the ocean, is the sea ice, or frozen ocean water. Now, my area of expertise and background is in sea ice. Glacial ice is somewhat different. Some of the issues are different, but there's also a lot of relations. But I will be telling you about something about the ice sheets as well. On the northern side, we have a different geography. Instead of a continent sitting on the pole, surrounded by ocean, we have continents surrounding an ocean sitting on top of the pole. So here the sea ice is sitting on the Arctic Ocean, and the biggest influence from the ice sheet side is the Greenland ice sheet there. So again, this is the cryosphere, and we're interested in how the cryosphere is changing. So I'm going to focus, as I said, much of the talk on sea ice, which is my area. And so why study sea ice? Well, it covers roughly 7 to 10% of the Earth's ocean surface. and it forms the boundary between the two principal geophysical fluids on the Earth, namely the ocean and the atmosphere. And as this thin frozen layer, it is not only an indicator, a leading sensitive indicator of climate change, but it plays a central role. It's a key player in our climate system. Here you see heat rising up through the ship's track of, so this is that's the lifeboat of the Aurora Australis that I've now been on 3 times. And this is, you see heat rising up through there, and evident by the moisture. So one of the most important roles that the polar ice caps play in the climate system is in reflecting incoming solar radiation, particularly during their polar summer. In some sense, Earth's refrigerator. Here's, roughly speaking, white snow and ice reflect most of the incoming radiation as measured by what's called the albedo, which is the ratio of reflected sunlight to incident sunlight, as opposed to ocean or land, in particular ocean, which absorbs most of the incoming radiation, so its albedo is very low. Here you see the northern polar ice cap reflecting most of the incoming radiation, but if a lot of that ice is gone, well, instead of getting reflected back, it's getting absorbed. So these are some photos from the Arctic, the Antarctic, and so from these photos, you may think that sea ice is just a barren, impermeable cap. However, sea ice is actually a porous composite material, pure ice with brine, air, and salt inclusions. Here's the salty water fluid inclusions on the sub-millimeter scale. This is a scanning electron micrograph showing sort of these things really in high resolution. Here are some vertical section of brine channels, so it's pictures I took in the Arctic. Here's a horizontal section showing this beautiful structure where, and these channels carry a lot of fluid that can move up and down through the ice, which turns out to be very important. Now, the volume fraction and the conductivity of the brine phase changes significantly with temperature. In particular, here you have sort of low volume when the ice is very cold, low volume fraction, disconnected brine inclusions, and they start to become connected up and increase in their volume fraction, and then you have lots and lots of pathways. This is actually some X-ray tomography methods, or some results of some X-ray tomography that we did several years ago to try to get our hands on and be able to really nail down the structure of this brine phase. Now, as I said, fluid can flow through this porous microstructure, and it turns out this turns out to be a really important process. Fluid flow through porous sea ice mediates key processes in both polar climate as well as the ecosystems that are there. Here you see melt ponds on the surface of Arctic sea ice. This is a photo I took in the Arctic in the springtime. Here's from a helicopter showing a very beautiful structure. Here's algal communities that live in the brine inclusions in sea ice. Here you see a brine inclusion with an algal cell in there. So this fluid flow through porous sea ice is very important for both the formation and melting of sea ice, ocean ice-atmosphere exchanges of heat, brine, as well as carbon dioxide, and also very important for, say, nutrient replenishment for the growth and decline of microbial communities. So what's this talk about? First, I'm going to discuss sea ice in the climate system, global climate model, give you just a tiny overview of global climate models, and in particular, the dramatic declines we've seen in the Arctic summer ice pack. I'll talk a little bit about, not too much, but a little bit about the melting of the great land ice sheets in the Arctic and the Antarctic and the relationship with the sea level rise, which I'm sure many people are interested in. I'll talk about fluid flow through sea ice, geophysical and biological processes associated with this, and some of the microphysics and some of the math we're using to try to help understand this. And then how do we monitor these processes? How do we get better information about these key processes that need to be understood better to improve our climate models through electromagnetic remote sensing? And then finally, I'll start moving towards Antarctica and tell you about some of the experiments we've been doing on fluid and electrical transport in sea ice. And in particular, I'll show you some photos from the expedition we were just on in November, December of 2010, just recently. And then I'll show you a DVD that I produced of our 2007 Antarctic expedition. So some of the mathematical themes of the talk, even though much of the math has been removed, there's still a lot of math, and I'm still a math professor. and there's a lot of mathematical ideas and concepts running through the talk. In particular, my formal training has nothing to do with sea ice or climate or anything like that. My background is in applying several complex variables, functional analysis, topics like this to composite materials. And when I look at sea ice, I see various composite structures on many different length scales. Critical behavior, where small, and this is one of the central ideas that's going on, that's happening, as well as how we approach this. Small changes in system parameters can induce large changes in behavior, such as phase transitions, like melting of ice. I mean, if it's a half a degree centigrade, well, it's water. If it's negative a half a degree centigrade, it's ice. So these tiny changes can induce, already at the very most basic level, induce significant changes in the overall behavior of the system. Linkage of scales. How do smaller scales influence larger scale behavior? This is one of the central technical scientific challenges of understanding climate change, as well as a lot of areas in science. The math doesn't care if a composite has microstructure on millimeter, meter, or kilometer scales. I see composites all through when I look at the sort of the climate system, and in particular the cryosphere. I've had a lot of collaborators in this research that we've been doing. Not the penguins here, but these other people up here. So at the University of Utah, we had a lot of people in the math department, and also recently been involving people in electrical and computer engineering, various postdocs, graduate students. I've now brought, I think, 6 undergraduates through our National Science Foundation funded research experiences for undergraduates, bringing math and lots of other students in lots of other areas, because as you'll see, this is a highly interdisciplinary area that we're working in, bringing up to the Arctic, and I've now brought a couple of undergrads down to the Antarctic as well. One of the main projects we're involved in is a joint project with University of Alaska Fairbanks, and Hayo Aiken is one of my main colleagues there. Also, Victoria University, New Zealand, and we have as you'll see, very strong connections with the Australian Antarctic program as well. So just a word about sea ice formation. This is what sea ice looks like. This is called nihilus. It's almost translucent. It forms under very quiescent conditions. And here, of course, you see these big icebergs from the big ice sheets hanging out there as well. So seawater freezes around a temperature of about minus 1.8 degrees C. If you look at the ice-water interface and you blow it up, you see this kind of corrugated platelet structure. And as the ocean freezes, it tries to reject the salt. You can't incorporate that into the crystalline structure of the ice. And so there's a highly concentrated layer of very salty water in front of this advancing ice-water interface, and the highly concentrated salty water gets trapped in these inclusions between these pure ice platelets. And this is showing some of the crystallographic structure of the ice as you move down through there, and this is a beautiful cross-polarized image showing some of that crystallographic structure. Actually, this is a photo I just took in the Antarctic just a couple of months ago. So this process of brine expulsion as the sea ice forms results in water beneath the ice becoming cooler and saltier, and this dense water sinks rapidly, and then this process of deep water formation drives circulation in the world's oceans, sometimes called the global thermohaline conveyor belt, which is one of the ways that the polar regions communicates with the rest of the world ocean system. In more turbulent conditions, you get this pancake-type formation. Very beautiful kind of structure. And again, I see a composite structure with the microscale being on about the meter scale. And you can see sort of waves. And you'll see some really cool video of these waves moving through fields of pancake ice. Now, sea ice is also very interesting in the sense that it displays multi-scale structure over 10 orders of magnitude, from the submillimeter scale of the brine inclusions to the polycrystalline structure, very similar to metals. Here's some of the brine channel, horizontal cross-sections of brine channels. And then here's some really big channels here. This is really hard to do. There's like this massive chainsaw that these guys have, or that David Cole has up in Alaska, where it's like the bar is about from here to here, and it runs on train tracks, and they go, and then they move it over an inch, and then they have like a crane to pull this massive ice sheets out, so you can see these incredible connected brine structures. Here's some of the pancake ice in the Southern Ocean and starting to congeal there. And here's larger scale flows. This is now looking from the, again, composite structures I see. There's the Aurora Australis, which is about the length of a football field. And then here's looking from space off the coast of Japan. And basically looking at, again, I see sort of a two-phase composite of ocean and ice, which is time evolving. Now, as I'm sure many of you are aware, you've seen fractals. So fractals have a beautiful self-similar structure on many length scales, and the sea ice pack is a fractal. One of the important issues is it's not just because it's beautiful, but the actual understanding the flow size distribution, the relationships between perimeters and areas are very important in climate models for looking at different kinds of melting and so on. Roughly speaking, bigger flows are easier to break and smaller flows are easier to melt. This is a fractal going back to the Greeks. This is the so-called Sierpinski Gaskin, and this is a naturally occurring fractal, also known as cauliflower. So here are some images showing the self-similarity of sea ice flows, sort of blowing this. This is the Polar Stern, the main German icebreaker. Now you blow this up and you sort of see a very similar kind of flow. And it turns out that there's sort of two regimes for a fractal dimension, for relatively smaller flows and then for much larger flows. Fractal microstructures also appear in composite structures that we study in sort of separate research. But again, in my mind, this is all kind of related to each other. We have a very large program applying statistical mechanical ideas to electrorheological fluids, where you have, say, metal spheres in oil, and you apply an electric field, they start to chain up, and then you get, within milliseconds, you induce a fluid-solid transition in this system, in this suspension. And when the spheres are metal, you get these beautiful fractal structures, which, again, are very reminiscent to the cross-sections, horizontal cross-sections of brine channels, which is also reminiscent of a purely probabilistic process called diffusion-limited aggregation, which also appears throughout science and engineering. So, let's talk a little about the meltdown in the Arctic and some of the shortcomings of these global climate models. So one of the things that's made the news a lot is the dramatic decline in the summer Arctic ice pack. And why is that important? Because, well, if that ice is not there in the summertime, the Arctic Ocean is absorbing solar radiation rather than reflecting it back. And so this dotted line is the average, about a 20-year average from 1980 to 2000. And then there was a general decline, sort of a general decline here, and then things sort of fell off the table in 2007 to a record minimum with a record decrease. Things bounced back, but now this last year in summer of 2010, it's dropped back down again, even below this trend line. To put this in some geographical perspective, back in about 1980, the aerial extent of the summer Arctic ice pack, and notice the ice is right up against Alaska there, and so all the polar bears that are living along there, they could use the ice as their hunting grounds the way they normally do. It turns out that the aerial extent here corresponded to the area of the continental U.S. without Arizona. Nothing against Arizona, that's just the way it came out. And so by 2005, we'd lost this area in red, amazingly corresponding to the continental U.S. east of the Mississippi, but then even more surprisingly, within the next 2 years, this huge swath of the Midwest of similar aerial extent. And now, the thicker multi-year ice that was so famous with these massive ridges and so on, that stuff's disappearing as well. So this is back at only just as recently as 2004, thick multi-year ice. You can see now just 4 years later, most of that's been replaced by much thinner first-year ice, which is then much more susceptible to melting and atmospheric and other perturbations of the system. Now, when you start looking at volume as well, the sea ice thickness is not so easy to get your hands on for many reasons. Microwaves get absorbed, for example. Microwaves from satellites get absorbed by the salty composite nature of sea ice. So there's been a general decline in the volume of Arctic sea ice, and this last year in 2010, again, things sort of fell off the table in terms of the volume, which in some sense is more important than just the aerial extent itself. Now, the Antarctic ice pack is already seasonal. You've got this big ring of sea ice surrounding the Antarctic continent, and most of it disappears, except for mostly in the western Weddell Sea, where Shackleton was, and that was actually the site of my first Antarctic expedition in my senior year of college, to precisely that region. And so I like to put the question, well, is global warming Antarctifying the Arctic? Is the Arctic turning into kind of a seasonal pattern like we already see in the Antarctic? And one of the main questions there is, can Arctic sea ice rebound? Or have we passed a critical threshold, a so-called tipping point, in a transition from an ice-covered to an ice-free Arctic Ocean? And there's been a lot of really interesting dynamical systems analysis where people make very general ODEs, ordinary differential equations, describing the albedo and the ice and how the interactions and so on. And there's a very beautiful piece of work by Ian Eisenman and John Wetlaufer showing that it's unlikely that we've passed through such a tipping point in a transition from current perennial sea ice to seasonally ice-free, although if there's much further warming and we get a loss of wintertime ice as well, that there may well be a tipping point. And there's been some really interesting new work on this just very, very recently. Mark Cerise, who's a quite prominent scientist in this area, who's also the director of the National Snow and Ice Data, said as recently as in September, after viewing what happened last summer, I stand by my previous statements that the Arctic summer sea ice cover is in a death spiral. It's not going to recover. Anyway, there's a lot of varying opinions on this, when it might happen and so on. But okay, so in any event, no matter how you look at it, climate change is being amplified in the polar regions. Global climate models predict that, well, if you're going to get some maybe a 1 degree rise over a certain number of years, say at the equator, you have to multiply that by a factor 2, 3, or 4 to describe what's happening in the polar regions. Now, what I want to do right now is just show you a couple of NASA clips. So let me just put this down here, and then go into here. And first, I'm going to show you how temperatures have increased in the Arctic. Now, this thing runs pretty fast, so I'll do the best I can to. So the colors in red will be showing the increases that you've seen in degree kelvins per year. So this is over about a 30-year period, sort of showing the warming that we've seen in the Arctic. And this is this polar amplification effect. And then let's take. Let's see. Yeah, so we're talking about a half a degree. Yeah. So now let's look at. So you see that the sea ice is almost like a living, breathing entity. This is kind of a cool one as well. So this is just the last summer, showing what happens during the summertime, how it melts back in the summertime. And there's one thing I want to point out, so I'll stop the. So that's Barrow, Alaska. We're going to be there in about 2 months, and I've been there many times. It used to be the ice would go up, basically go up there. And again, like for the polar bears that live there, now you see their hunting grounds are, well, a few hundred miles away now. Okay. All right. So, what's also kind of surprising is that the world's best climate models have significantly underestimated this dramatic decline that we've seen. So these are the predictions of the last round of IPCC projections, and here's sort of the range of averages of these models. Here's all these averages of runs. They all predict a general decline of summer Arctic sea ice. Whether or not the sea ice will disappear within 40 years or 20 years or by the end of the century, they all vary. But what's kind of dramatic is, well, that's the actual data. That's what we've seen, is that none of the models have been able to capture the degree of melting that we've actually experienced in the Arctic. Now, something that may be on your mind is, okay, well, all this ice is melting, all this sea ice is melting. Does that contribute to sea level rise? Well, the answer is no. Not directly, at least. So this is a photo I took in the Antarctic, sort of glacial ice, these icebergs floating, and here's the very thin sea ice. So icebergs and the great ice sheets are a couple of miles thick. These are massive over an entire continental scale, and the sea ice itself is maybe a few meters thick. And when you freeze ocean water, well, it becomes less dense and it floats, and then when it melts, it goes back down, and it just doesn't change sea level at all. Sea ice is in isostatic balance with the ocean, and it doesn't change sea level. However, when you remove sea ice from some area, well, you're getting more solar absorption and things change and currents change and so on, and that can indirectly, and these feedback effects can indirectly influence the issue of sea level rise. So now I want to tell you a little, at least, about the great ice sheets. So as Earth's climate warms, why does sea level rise? We've seen over the last century about a 20 centimeter rise in sea level, and most of this is occurring from melting land ice, such as Antarctica, Greenland, mountain glaciers. But also there's a thermal expansion effect. As the ocean warms, it expands. And this accounts for about 25% of the rise in the last half of the 20th century, although this rate has about tripled in the last 10 years or so. There's another aspect called continental rebound that as the land masses that originally were depressed by huge weights of ice, as they rise up, now you're starting to mess with the continental plates. And in fact, actually, this is actually showing the British Isles what's actually happening. How this part's rising, this is sinking. And actually, I was reading in another book actually about large waves, about another one of my favorite topics is rogue waves and tsunamis and things like that. And they were discussing how when you start moving tremendous amounts of water around and changing the weight distributions on the Earth, how you can get increased tectonic activity. So it is conceivable, and at least there seems to be significant scientific support, as ultimately if you say add a meter to sea level, that you could get increased tectonic activity, more volcanic activity, perhaps underwater landslides, and so on. So there's perhaps unexpected consequences of the rise in sea level and the retreat of these ice sheets. And of course, there's also runoff from rivers and streams as we move ahead. So here's the Greenland ice sheet showing thinning around its fringes. Here's the Antarctic. That's the Greenland ice sheet. Here's the Antarctic ice sheet, which is over here actually seems to be a net positive balance. I'll talk about that in a minute. But what everybody's concerned about is the Western Antarctic ice sheet and its potential melting and collapse. Now, if all the land ice melted, which certainly is not going to happen tomorrow, Antarctica would contribute about 57 meters to sea level rise, Greenland about 7 meters, and mountain glaciers about half a meter. The major concern here is the West Antarctic ice sheet, which would, if it all melted, would contribute about 7 meters. And here's these pictures that you've seen of how Florida would be inundated. This is with a 6-meter rise, and of course that would all be underwater. Now, some of the mechanisms for exporting glacial ice into the ocean. Here you see what are called moulins, these cracks or crevices in with meltwater then sort of collecting, draining down through here, moving through the ice, lubricating the ice-rock interface, which then facilitates glacial flow and export of this ice out to the ocean. Similar, from my perspective, to fluid flowing through the microstructure, the porous microstructure of sea ice. Now, this is some beautiful shots of calving and breakup of ice shelves and tidewater glaciers. In some sense, breaks when you get a breaking off of this ice shelf, you get some of the effect is that you're breaking like the log jam, which could facilitate further ice flow. And they speak of glacial conveyor belts, which is the primary mechanism. Here's a big glacier draining out into the ocean. Primary mechanism for draining ice sheet interiors by delivering icebergs to the ocean. Now, here's something close to my heart. In 1999, I was on the Mertz Glacier polynya experiment to look at the polynya. So a polynya is an ice-free region. Here, the effect was these katabatic winds come screaming across the continent and blow the ice out, but it's winter, so new ice forms. Winds blow the ice out. New ice forms. These are like ice factories around the coast of Antarctica, these polynyas, coastal polynyas. And in particular, we spent a couple of months in this region near Buchanan Bay at the Mertz Glacier tongue. Well, in last February, I guess just about a year ago, it broke off. This big iceberg, B9B, crashed into this guy and then broke it off. And so that's another mechanism that will be contributing to the outflow of ice into the ocean. So one of the central concepts here is the mass balance of ice sheets and glaciers. It's positive if there's more accumulation happening up high than melting. Negative if there's more melting than accumulation. Here's the turned into meters of water equivalent for glaciers throughout the world. And you can see a general decline, a pretty steep decline, over the past, say, 40 years or so. Small glaciers, there's a negative net balance of about 400 gigatons per year, contributing about 1.1 millimeter per year of sea level rise. 1 gigaton translates into 1 cubic kilometer of ice or water, ultimately, and with the change in density, of course. And Greenland, in the 1990s, about a negative 100 gigatons per year, up to around 200, 2006, although there's an incredible degree of uncertainty and variability in these. These are hard things to measure. And let's see. And then in Antarctica, about, I guess, according from this work, about a negative 100 in the 1990s to overall negative 200 in 2006. But then Jay Zwally, who's in charge of the ICESat program for NASA and was my high school mentor when I grew up right near NASA, worked with him for about a year or so. Negative 47 for the western Antarctic ice sheets, plus 16 in the east, but negative 31 overall. So overall, there certainly appears to be a net loss of ice in these glaciers and ice sheets. This is the Jacobshavn Glacier, which is does the largest drainage for the Greenland ice sheet, showing its particularly rapid in the last several years. This is what over. That's about 50 years, and here's a similar distance. That's about 6 years. And this glacier moves very rapidly, actually, with top speeds of. You think about glacial movement, thinking very slow. Here we're talking about 35 meters per day at its top speeds. So ice sheet and glacier modeling in climate projections is not mature. It's much more mature in sea ice, actually. There's no coupling yet of ice sheets and ocean in climate models. There's none of the important feedback effects that have been incorporated. One particular important thing is the interaction of warm water with the periphery of large ice sheets represents one of the most significant possibilities for abrupt change, like critical behavior in the climate system. And it's also that calving and ice sheet breakup is just not well understood. And this is in my discussions with David Holland, who's the director of the Atmosphere Ocean Center at Courant Institute from New York University, and is becoming a world expert on the issue of sea level rise and modeling ice sheets and modeling some of these interactions, actually, and getting them into climate models. So now let's turn to sea ice models. So what's essential in a sea ice model for climate studies? Well, you want to simulate the climatological mean annual cycle of the ice and the snow. You need to have the key feedback effects and represent sensitivity to perturbations. And the physics has to be appropriate to the model spatial scale with parameterizations for processes that are happening on much smaller length scales, which is one of the big challenges, this linkage of scales that I was talking about before. So what are the key ingredients or governing equations that need to be solved for these big models? Well, one of the main things is the ice thickness distribution evolution equation, which involves both the dynamics and the thermodynamics of the ice. Conservation of momentum, essentially F equals ma for sea ice, and the heat equation of snow and ice, which couples the ocean to the atmosphere through this important layer of the sea ice, the thermodynamics. You can dynamically modify the ice thickness distribution through ridging and or divergences in the ice field, thinning and thickening. This can take away from the mass from that probability density that you're solving that partial differential equation for, or increase mass at in certain areas of thickness. These are some photos I've taken in the Antarctic. I like to view sea ice dynamics as like plate tectonics on a fast time scale. This was like a little mountain ridge that was formed in front of my eyes in about the space of a half an hour. This used to be our main street it was supposed to have been a 10-day drift camp, but it turns out we were in a big shear zone, and so everything got completely ripped up, and I get to go out and use a big steam drill to pull some of our instruments out, and it was a dicey night, but fortunately nobody was hurt, and everything. We recovered most of the equipment. So what must we understand better about sea ice processes and air ice ocean interactions to improve climate projections? In particular, what must be represented more realistically in these models? Well, one main effect, as I've sort of alluded to, is this ice albedo feedback. Here's melt ponds in the Arctic. You get melting. That lowers the albedo, which means you absorb more sunlight, which means you get more melting, which lowers the albedo, and so on in a positive feedback loop. And this, of course, happens on the larger scale in the ocean as well, as we lose more ice. Now, ice albedo feedback played a key role in the 2007 decline. Ice mass balance observations showed an extraordinary amount of bottom melting in the Beaufort Sea. Calculations indicate that solar heating of the upper ocean was the primary source for this observed melting. And this increase in open water fraction, as I've been alluding to, resulted in a 500% positive anomaly in solar heat input into the upper ocean, which triggered this ice albedo feedback. Now, on the ice itself, the ice albedo is determined by these beautiful melt ponds here. This is actually a photo of me wearing my frogman suit, because the melt ponds were so deep that most of my colleagues there wear these boots. I have this green rubber suit, so I somehow became known as Frogman. And so I was asked to go out and do there's a big transect along here. I'm doing thickness of measuring the depth of these melt ponds. And so the evolution of the melt ponds, whether or not they pool up or drain, is constrained by how easy it is for fluid to flow through this porous microstructure of the sea ice, which leads us to one of the central things that I've been studying, was the fluid permeability of the ice itself. There's also larger scale porous media issues. This is a drainage vortex. So basically, if you stepped over there and you slipped on the ice, you just get sucked down, and that's the end of you. Because you're not going to be able to get back out from there, and you'd have to sort of swim around in minus 2 degrees Celsius water. Of course, you can only live in that for about a minute, and before your muscles completely seize up. And so, anyway, so melt pond evolution. There's a lot of ways to die when you're doing when you go on these expeditions. Believe me, I've been in a lot of dicey situations. Melt pond evolution depends also on these large-scale pores in the ice cover. Where do they come from? Well, first of all, this is showing drainage over the large scale, and so the connectedness of these melt pond structures is very important, determining the scale over which these holes are acting. Where do they come from? Seals. So this is, a seal that's keeping his hole open so he can get up there. So this is an interesting sort of biophysical aspect of all this. Now let's focus on the larger sort of issue here, which is the sea ice microphysics, which is determining so much of what happens in these systems. So one of the main things that I've discovered in my career is, in some sense, the on-off switch for fluid flow. And this is critical behavior of fluid transport in sea ice. So as the temperature increases, the brine volume fraction increases. And it turns out that for brine volume fractions below about 5%, the sea ice is effectively impermeable. And for brine volume fractions above that, the sea ice is increasingly permeable, allowing fluid to flow. This critical brine volume fraction corresponds to a critical temperature of minus 5 C for a typical bulk salinity of 5 parts per thousand, hence the rule of fives. Now, why is this important? Well, one reason is snow ice formation. In fact, this is where I sort of discovered, at least realized that, hey, this is something that's important. I was out in the middle of a storm, winds blowing about 60 miles an hour, about midnight in 1994 on the Ansplex expedition, where we were the first winter cruise to go into this region, this big hole. And in the ice, although we didn't see a hole, we saw a dynamic equilibrium of ice. But one of the main effects was you're getting melting from the bottom, but then how are you replacing that ice? Well, I was out in this storm. I saw seawater, all of a sudden, seawater percolating up and flooding the surface. And that slushy mix, then when the storm goes away, it freezes. And so it's like backwards sea ice freezing. But this turns out to be really important. It accounts for about 25% of the ice that's produced in the Antarctic. And the moment I saw that, I had just spent the previous 10 years of my life proving abstract theorems about so-called percolation models, which I'll tell you about in a second. And I realized that's percolation. That's a phase transition, which is controlling this very important process. The permeability of the ice also constrains the evolution of salinity profiles, which currently are assumed to be constant in climate models, which is a major drawback of what's happening in these models. Convection enhanced thermal transport. As you move brine around in the ice, you are helping exchange heat, and it also affects microwave signatures in remote sensing, as you might imagine. But also, it's biologically very important. Here's a snapshot of the sea ice ecosystem with the killer whales eating the penguins and the penguins eating the krill, little shrimp-like critters, and then they subsist off the algae that lives inside the fluid inclusions in the sea ice. And you get these beautiful colors like this, and there's greens and all sorts of other colors. Now, the nutrient replenishment processes are controlled by the permeability of the ice, and in particular, biological activity in the sea ice turns on or off according to my rule of fives. Here's an example of this critical behavior. This is convection-fueled algae bloom in Ice Station Weddell from 1992. Here's ramping up, and then it shuts down. And that 2-day period where the kink in the data is precisely when the critical isotherm, below which you're permeable and above which you're impermeable, passed through the bottom of the algae layer. So from that point on, they were stuck with what they got. There was no new influx of nutrient-laden seawater. Sea ice and these kinds of issues are also important for astrobiologists. There's been a lot of speculation, for example, about Europa, which is covered by sea ice. And are there algae or there are other kind of life forms that could potentially exist in the fluid inclusions in their sea ice? So now a little bit about some of our theoretical ideas that we've been using here. Darcy's law for slow viscous flow in a porous medium relates the average fluid velocity to a pressure gradient, and the thing that relates them is this, what I would call a fluid conductivity, the ratio of the fluid permeability tensor divided by the viscosity. This is an example of what's called homogenization, a branch of mathematics where a lot of my formal training is in, mathematics for analyzing the effective behavior of heterogeneous systems. Now, before our work, even though this issue of fluid permeability and fluid flow in sea ice is so important to the biology and all these other important processes for climate studies, there were just a few measurements and essentially no theory of this. So we developed a full-blown, multifaceted theory of the fluid permeability in sea ice based in homogenization and Darcy's law, rigorous bounds, percolation theory, hierarchical models, network models, all validated with laboratory and Arctic field data. And in particular, before our work, people had relied pretty much on sectional photos to analyze the brine inclusions in sea ice. And we developed an X-ray CT imaging way of looking at this, which provided a really unprecedented look at the thermal evolution of the brine phase, and in particular, its connectivity. This is the cover of Geophysical Research Letters, showing, from my perspective, homogenization in action, how the microscale, some of our X-ray tomography, controls these larger scale issues of importance to global climate, such as the evolution of melt ponds. So I just want to say, so a lot of my early work is based on finding rigorous mathematical bounds on effective transport coefficients of composite materials. So there had been actually not much work on this for at least what we were looking for porous media. And it turns out that if you want to maximize the vertical permeability, vertical pipes with appropriate radii maximize that vertical permeability and has kind of a hierarchical type of structure, which I'd call ice pipes with brine in them. This is the fluid analog of the so-called arithmetic mean upper bound for effective conductivity of composites, just the arithmetic average. There was some beautiful work of a colleague of mine, Sal Torquato at Princeton, who derived a more general set of bounds, and it turns out that our bounds that we were working are a special case of his bounds. We get these bounds through a variational analysis of the so-called trapping constant for a diffusion process in the pore space with absorbing boundary conditions, so that's sort of for the mathematicians and physicists in the audience. I thought we'd be, with such a simple idea, I thought we'd be orders of magnitude off. I thought it would be a bound, but we closely captured all of our laboratory and Arctic data. Now to specific predictions of the permeability of the ice. So our main tool is percolation theory, something that I've worked in as a mathematician for many years. The mathematical theory of connectedness. You start with, say, a 2D lattice. A bond is open with probability P, closed with probability 1 minus P. This is P equal 1/3. This is impermeable. Fluid or electricity might try to get through here, but it can't. Now, P equal 2/3, now we're permeable. It might be a tortuous pathway, but you can get through. For this 2D model, this 2D square lattice, the percolation threshold is rigorously known to be 1/2 or 50%. which is where you have the first appearance of an infinite cluster in an infinite version of this. Now, the first question, though, is, well, why is the percolation threshold, what we think would be a percolation threshold, why is it 5% in sea ice, which is very different than the classic lattice models? So my first observation in this area was to simply observe that the microstructure of sea ice was very similar to so-called compressed powders, which were used in the development of stealthy or radar-absorbing composite materials, where they were randomly mixing up carbon black or silver particles into a polymer host to achieve conductivity and the desired radar-absorbing characteristics. And then they came up with this great idea in a paper in Nature back in the late 1960s, I think, or early 70s, that they could use big polymer spheres and little metal particles and then squash it together, and they could achieve the desired conductivity and get much, much lower critical volume fractions. So I used their so-called compressed powder continuum percolation model, simply applied it to sea ice, and out popped the 5%, which explained all sorts of data on ice production and algal growth. It was conjecture at the time. I mean, I felt it in my gut that this was true, but I had no direct evidence that this was in fact going on. Now that we have our X-ray tomography, we can really show, yeah, it's right. So here's some of our X-ray tomography. We take 3D images of pores and throats, map that over to 3D graphs of nodes and edges, and then analyze the graph conductivity as a function of temperature and sample size, and use so-called finite size scaling techniques in physics to actually confirm my rule of fives. These are the order parameters in percolation theory. The correlation length, the characteristic scale of connectedness diverges as you approach the critical point with a universal critical exponent. The so-called incident cluster density, where there's no incident cluster below the threshold, and it takes off with a universal critical exponent. Universal means it doesn't depend on the details of the lattice. It only depends on the dimension that you're in. It captures the deep physics that's at the heart of a phase transition or behavior. Now I've seen hundreds of papers where they compute these functions lattice model. I've never seen a paper in the literature where they actually do this real materials. You can't turn a knob, for example, and change the conductivity of pores in sandstone. But in sea ice, they can do that. Change the temperature, dramatic change in the conductivity and volume fraction of the fluid pores. So this is real data on the divergence of vertical correlation length in sea ice as you change the temperature. Here's some of our X-ray tomography. This is now our theories of the fluid permeability using lattice and continuum percolation theory, where we by analyzing the kinds of distributions that we have for the brine inclusions in sea ice, we can conclude that even though in the continuum you can get so-called non-universal behavior with non-standard critical exponents, in sea ice we should be seeing, amazingly, the universal lattice value of 2, about 2 in 3 dimensions, which again something I did a lot of work on earlier in my career. And so this is our deceptively simple prediction for a simple formula for the fluid permeability and how it depends on volume fraction. And this scaling constant in front we actually compute as well using so-called critical path analysis, which was originally developed for electronic hopping conduction in doped semiconductors. And so again, we get this universal lattice critical exponent. This is our prediction here. Here's some of the raw data taking off above 5%. And then here's our theoretical prediction and the statistical best fit of the data, so you can see that we're quite close. We wanted to get a more general theory, which would work for a broader range of brine volume fractions, not just right near the percolation threshold. And we used a hierarchical model of brine-coated spherical ice grains, which had been used for porous media, an even simpler looking formula, which has been really good for these climate models because these are easily parameterized. And here's our theoretical prediction from the hierarchical model and the statistical best fit of the data, which matches up very well. So I wanted to mention that cores from these land ice sheets are used for getting big long-term climate records, such as on CO2 data, which has been very important in the development of climate science, and through the analysis of the bubbles in there. And it turns out that percolation theory, as noted by Enting in Nature in 1985, percolation theory gives the critical depth below which the air bubbles are disconnected from the atmosphere. If you're going to analyze the gas and try to figure out what was happening 100,000 years ago, you need to make sure that those bubbles are not connected to the current day atmosphere. And percolation theory does this for you. Larger scale critical behavior. This is the onset of melt ponds and the pond fraction. It just sort of takes off, to me, like an easing model if you're in physics. A model for the critical point for a ferromagnet. It's a very similar kind of process. I believe that there's a threshold in the connectedness of the melt ponds. Here the ponds are disconnected, the ice is connected. Here there's a biconnectedness, ponds are connected, ice is connected, and here the ponds are connected and the ice is disconnected. And we're using, again, methods that I've been looking at for years on larger scales now to analyze this kind of problem. Another example of critical behavior, the famous collapse of the Larsen B ice shelf. Stable for 12,000 years, disintegrated in a month. Formation of melt ponds on the surface, that water seeps down, starts to freeze, wedging it open, and then there's warmer water from the bottom, eroding it from the bottom. The thing disintegrated in a month. Here's again a nicer picture of this with these melt ponds on the surface, helping to speed up the process. Now a bit about remote sensing, how we're trying to electromagnetically monitor these kinds of problems. The key parameter in the interaction in modeling the interaction of an electromagnetic wave with a composite material is the so-called effective complex permittivity or complex dielectric constant, epsilon star, which depends strongly, in this case, on the brine microstructure. And this is, again, an example of homogenization, where we have an inhomogeneous medium, and the whole idea of homogenization is to mathematically construct or find the homogeneous medium, which behaves macroscopically the same as the inhomogeneous medium. It involves solving partial differential equations and a lot of other kinds of mathematics that we employ in this business. Kind of similar in spirit to ocean swells propagating through a vast field of pancake ice. Here, you look at the microstructure, you get these meter-scale pancakes, but a long wave doesn't see the individual flows. It sees an effective medium, which dictates its propagation characteristics. So, in the theory of effective electromagnetic behavior of composites, which we're using to analyze the sea ice and to monitor these processes, forward homogenization is where you know something about the composite geometry or a so-called spectral measure associated with this and derive formulas or information, rigorous bounds and approximations for the effective complex permittivity. And then there's the associated inverse problem, which is what we're most interested in now, to go backwards, where you take data, electromagnetic measurements, and you want to reconstruct information about the microstructure, which is what we're doing to monitor these processes and to, say, recover brine volume fraction, conductivity, and other characteristics of the microstructure. These are just some examples of these bounds in the complex plane. This is some of the inverse problem associated with this, where we can derive rigorous bounds on the brine volume fraction. Now, for this so-called random resistor network, or the percolation model, you can compute what is called a spectral measure for this, where the gap in the spectrum, it naturally lives on 0, 1. The area under this curve here represents the probability, 25%, the probability of finding one of these bonds, and the spectral gap indicates that it's disconnected, and that spectral gap disappears as the system becomes connected. And there's a lot of what's called random matrix theory that underlies some of our analysis here. My colleague Lena Cherkayev at Utah has been using these kinds of ideas to look at to estimate bone porosity from measurements of the effective torsional modulus using reconstruction of this spectral measure, ultimately to monitor osteoporosis. And from my standpoint, the math doesn't care if it's sea ice or bone or lungs or whatever kind of composite you're looking at. We've just recently published a paper in Journal of Biomechanics where we've computed the spectral measures and started new types of characterizations of bone microstructure. Here's healthy bone, osteoporotic bone, and you see these differences in the spectral measure. In sea ice, the porosity changes significantly with small changes in temperature, and if bone behaves similarly, you could just get osteoporosis from a fever or a flu. Here's our spectral measure calculations for the Arctic ice pack. This is the issue of upscaling. How do you incorporate subtle characteristics of this composite microstructure of the ice and ocean to larger scales. Here's a consolidated ice pack and its spectral measure, and very different spectral behavior for this loose ice pack. Now on to Antarctica. We're just about, in a couple minutes, I'm going to show you the video now. We were on the Sea Ice Physics and Ecosystem Experiment in 2007, which was one of the main activities for the International Polar Year. We measured electrical and fluid transport during SciPex to help monitor these fluid transport processes, and also for measuring thickness of the ice, which is important in gauging the impact of climate change. We made direct measurements, the first direct measurements of DC vertical conductivity from extracted ice cores. We did surface impedance tomography, like putting electrodes on your chest to tell what's going on inside. We actually made the first measurements of fluid permeability in the Antarctic ice pack, and we did tracer studies where we poured fluids through inverted ice blocks. This is some of our 1960s era electrical boxes, and here's our extracted cores doing electrical measurements with the aurora in the background. We found this is the big result here, is that we found from our direct measurements, we found the electrical signature of this on-off switch, my rule of fives, but for electrical conductivity. So that means there's a divergence of the resistivity 1 over the conductivity as you approach 5%. This is our Antarctic data. I then looked at my colleagues' Arctic data from a completely different method, and we see the same behavior. This is putting it all together. The electrical conductivity of sea ice has been studied for 50 years, but these are the first observations in theory of this so-called critical behavior, and it now opens the door to the use of electromagnetic sensors to monitor these key transport processes, which are important for understanding climate that I've been talking about. This is the electrical changes that you see with the onset of melt ponds, that there's really hope here that we can start to electrically analyze the evolution of these all-important melt ponds. Here's me doing my measurements of electrical, of fluid permeability. I like to call this all my friends down there have these multi-million-dollar instruments, so I call this my $1,000,000 meter stick. Here's pouring tracers through the microstructure of the sea ice. And then this last fall now, we went down to Antarctica with the New Zealanders, again to measure fluid electromagnetic and microstructural properties of sea ice. We were